Picture the map on your classroom wall. You've seen it 1,000 times, on posters in textbooks, in the little globe icon on a weather app, stitched into the opening titles of nature documentaries, and flashed behind 100 newsroom weather reports. A rectangle. Blue oceans, green and tan continents, thin black lines of latitude and longitude running straight across it like graph paper. Somewhere near the top, Greenland sprawls out enormous, almost the size of the entire African continent sitting just below the equator. You know this map. Your brain has filed it away as simply what the world looks like. Now imagine a shipping company draws a single straight line on that map, from the port of New York to the port of London. It looks obvious. It looks like the shortest way across. A ruler and a pencil connect point A to point B, and there you have it, the most direct path a vessel could take across the Atlantic Ocean. That straight line is lying to you. Not in some vague, philosophical, all maps are imperfect sort of way. It's lying in a specific, measurable, consequential way. And real ships making real crossings don't follow it. The vessel that actually takes the shortest path between New York and London does something that looks, on that same flat rectangle, like a mistake. It bows upward. It curves north, arcing toward Newfoundland and the cold water south of Greenland, tracing a path that looks longer on the page than the straight line does. And yet it's shorter. In the real three-dimensional world, the curved line beats the straight one every time. On every long ocean crossing where the 2 points aren't sitting on the equator or on the same line of longitude. That's not a rounding error. Depending on the route, sailing the straight line instead of the curve can cost a ship hundreds of extra nautical miles. On a very long voyage, at high latitude, the gap grows even larger. Multiply that difference by the fuel a modern container ship burns per mile. Multiply that by the thousands of ships crossing oceans on any given day, and you're looking at a distortion that has shaped the shipping industry, the fuel bill of nearly every nation on Earth, and even how sailors have died at sea for the better part of 500 years. The map isn't broken. It was never meant to answer the question you've been asking it. And once you understand why, you won't be able to look at a world map or a straight line drawn across an ocean the same way again. Let's start with the honest history of that rectangle, because the story of how it was built explains everything that follows. In the year 1569, a Flemish cartographer named Gerardus Mercator published a world map, Wada, with an extraordinarily long Latin title that, translated, reads roughly as a new and enlarged description of the Earth, adapted for use in navigation. Not an accurate picture of the world. Not a fair representation of the sizes of continents. Adapted for use in navigation. Mercator wasn't trying to give humanity a photograph of the planet, flattened. He was trying to solve one specific, brutally practical problem that had been costing sailors their lives for a couple of 100 years. Here's the problem. A ship's compass tells you a direction. Point the bow northeast and hold it there. That's easy to do, and easy to keep doing for days, because a compass needle doesn't drift or wander, and a helmsman can hold a heading with a clock they were watching anyway. But before Mercator, the charts sailors used, called Portolan charts, were built on simple flat geometry. They drew straight lines between ports based on compass bearings taken from experience and dead reckoning. And near a coastline, over short distances, this worked fine. The Earth's curvature barely mattered over a few hundred miles. Picture one of those Portolan charts for a moment, because they were genuinely striking objects in their own right, not crude sketches. The most famous surviving example, a lavishly illustrated work known as the Catalan Atlas, produced around 1375, likely by a Jewish cartographer and instrument maker named Abraham Cresques, working in Majorca, covers its parchment in a dense web of intersecting straight lines, radiating out from small compass roses scattered across the sheet. Each line representing a specific memorized compass bearing between two ports. the accumulated, hard-won knowledge of generations of Mediterranean sailors rendered as pure geometry. These charts were extraordinarily good at the job they were built for, threading familiar coastal and Mediterranean routes where distances were short enough that the Earth's curvature simply didn't bite. They were never built with the mathematics to handle a genuinely long, open ocean crossing, because for most of the era that produced them, essentially nobody was making one. Ocean crossings were a different story. The Earth is a sphere, or close enough to one for this purpose, and a straight line drawn on a flat piece of paper doesn't behave the same way once you try to make it correspond to a curved surface. Sailors following a constant compass bearing across a genuinely long stretch of open ocean, especially at higher latitudes, would find that the path they were actually tracing through the water wasn't straight at all. It was curving, spiraling very gradually, and their position on a flat chart based on old assumptions would drift further and further from reality the longer the voyage lasted. People got lost. Ships missed their destinations by enormous margins. Some never made it at all, and nobody could say for certain whether that was storms, disease, or simply sailing confidently in the wrong direction for weeks on end. Mercator's solution was a specific kind of mathematical trick, and it's worth sitting with for a moment because it's genuinely elegant. He built a projection, meaning a system for translating the curved surface of the globe onto a flat sheet that preserved angles. Wherever you are on his map, a compass bearing drawn on the paper matches the compass bearing you'd actually sail in the real world, exactly everywhere. In technical terms, this property is called conformality. In practical terms, it means something wonderful for a sailor. If you draw a straight line from your starting port to your destination on a Mercator map, and then follow that single, unchanging compass heading the entire way, you'll arrive. That specific kind of path, a line of constant compass bearing, has a name. Navigators call it a rhumb line, or sometimes a loxodrome, from Greek words meaning roughly slanting course. A rhumb line is beautifully simple to sail. You point the ship, you lock the heading, and unless wind or current pushes you off course, you hold that single bearing from departure to arrival. No recalculating. No adjusting the compass every hour. No advanced trigonometry required on deck. For sailors navigating with nothing but a compass, a chip log to estimate speed, and dead reckoning, this was transformative. It gave an ordinary crew a course they could hold across an entire ocean without recalculating a single thing, and it still deserves the credit it gets. But notice what Mercator's map had to give up to make that trick work, to keep angles honest everywhere on a flat rectangle, representing a round object. Something else has to stretch, and what stretches, dramatically, is area, and it stretches worse and worse the further you move from the equator toward the poles. Here's the part most people already half remember from a viral image or a well-meaning teacher at some point in their life. On a Mercator map, Greenland looks almost as large as Africa. In reality, Africa is about 14 times bigger. Greenland's true area is a little over 2 million square kilometers. Africa's is above 30 million. Side by side on the actual globe, Africa would swallow Greenland more than a dozen times over. But push Greenland up near the 80th parallel, where the map's east-west lines have to stretch enormously just to keep angles correct, and its outline inflates until it rivals a continent sitting near the equator, where almost no stretching happens at all. This wasn't a flaw Mercator overlooked. It's the necessary cost of the thing he was actually trying to build. The scale of distortion isn't random either. It follows a clean mathematical rule. The further you are from the equator, the more the map stretches you out, according to the secant of your latitude. At the equator, essentially no distortion. By around 60 degrees north or south, roughly the latitude of southern Greenland or Anchorage, Alaska, the map is already stretching things by a factor of about 2. Push further toward the poles, and the distortion accelerates without limit. which is also why standard Mercator maps simply stop somewhere around 80 to 85 degrees north and south. Keep the projection running all the way to the actual pole and the stretching becomes infinite. There's no way to draw the North Pole itself on a true Mercator projection. It doesn't exist on the page. The map runs out of paper before it runs out of planet. Gerardus Mercator himself is a more dramatic figure than the tidy textbook footnote most people encounter suggests. Born in Flanders in 1512, he trained as a mathematician, philosopher, and instrument maker before turning seriously to cartography. And in 1544, decades before he published his famous projection, he was arrested and imprisoned for several months on suspicion of heresy, a charge that in that period and place could plausibly have ended in execution. He was eventually released, in part because of testimony from colleagues at the university where he had studied, and he went on to spend the rest of his working life in the town of Duisburg, producing globes, scientific instruments, and increasingly ambitious maps, of which the 1569 navigational projection became, centuries later, by far the most famous, even though it was only one project among many in a long and varied career. It's also worth knowing that Mercator's projection didn't take over the world of navigation overnight, the way its later cultural dominance might suggest. For roughly 30 years after its publication, most working sailors kept using the older Portolan-style charts they already trusted, partly because Mercator never fully explained the mathematics behind his projection in a way other navigators could independently verify or reproduce, and partly because without that explanation, the projection looked less like a solved problem and more like an unproven claim from a single map maker. The turning point came in 1599, when an English mathematician named Edward Wright published a book called Certain Errors in Navigation, which laid out, in careful and rigorous detail, exactly why the older charts produced compounding errors on long voyages and exactly how Mercator's projection corrected them, complete with the tables of figures a working navigator would actually need to construct or verify the projection for themselves. Wright's book is, in a real sense, the reason Mercator's idea eventually won. A brilliant piece of mathematics sitting unexplained in a single wall map wasn't enough. It took someone showing the working, in language practical seafarers could actually check against their own hard-won experience before the whole maritime world was willing to trust it with their lives. That trust mattered enormously, because the era just before and during Mercator's working life was defined by exactly the kind of catastrophic navigational error his projection was built to prevent. When Christopher Columbus crossed the Atlantic in 1492, he was navigating with instruments and charts that had no reliable way to account for the Earth's curvature over long distances, and his estimates of both the size of the Earth and the distance he had actually traveled were significantly off. A fact somewhat obscured by the accident that a previously unknown continent happened to be sitting roughly where he expected to find the coast of Asia. Ferdinand Magellan's expedition, which completed the first circumnavigation of the globe between 1519 and 1522, suffered horrifically from cumulative navigational uncertainty across the vast, uncharted stretch of the Pacific, running so low on food and fresh water during a crossing that took far longer than anticipated that sailors were reduced to eating leather and sawdust. And the fleet that limped home was a fraction of the size and crew that had set out. These weren't failures of courage or seamanship. They were failures of the underlying mathematics available to translate a curved world onto a chart a human being could actually use. Exactly the gap Mercator's later work was aimed squarely at closing. There's a small piece of naming trivia worth knowing here too, because it shows just how thoroughly Mercator's influence spread beyond his own famous projection. Late in his career, Mercator compiled a bound collection of maps and, on its title page, depicted the mythological Titan Atlas holding up the heavens, choosing that image as a fitting symbol for a book meant to hold up the whole known world in map form. The name stuck permanently. Every bound collection of maps in every language since has been called an atlas. a word that traces directly back to a single publishing decision made by the same cartographer who solved the compass-bearing problem for ocean-going sailors. So that's the size illusion. And if that were the whole story, this would be a fairly well-worn topic. Plenty of documentaries, plenty of viral infographics have made the Greenland versus Africa point already. And by itself, it's a curiosity, a fun fact for a pub quiz. What most of those retellings leave out is the far more consequential twin of the size illusion. That's not really about how big countries look. It's about how straight lines look instead. And that's the illusion that actually reaches out of the map and changes what happens on the water. Because here's the thing about a conformal projection built to make compass bearing straight. A rhumb line, that constant heading path so beloved by sailors with nothing but a compass, isn't, except in two very specific cases, the shortest distance between 2 points on a sphere. The shortest distance between 2 points on a sphere is called a great circle. And a great circle is a very particular kind of curve. It's the path you'd trace if you sliced the Earth exactly in half, through its center, through both of your chosen points, and then walked along the rim of that slice. Every great circle divides the globe into two equal hemispheres. The equator is a great circle. Every line of longitude paired with its opposite meridian on the far side of the planet forms a great circle too. Those are the only rhumb lines that also happen to be great circles, because they're the only compass courses, due east along the equator or due north or south along a meridian, that don't have to bend as they cross the globe. Everything else, any journey that runs some mixture of east-west and north-south direction, produces two different answers depending on which kind of path you choose. The rhumb line gives you a constant compass heading and a straight line on a Mercator chart. The great circle gives you the shortest possible track through real space and, when you plot it on that same Mercator chart, a curve that bows toward the pole. Let's make this concrete rather than abstract because the difference isn't trivial and it isn't the same everywhere. Take our earlier example, New York to London. These two ports sit at a fairly similar, moderate latitude, and the route runs mostly east to west, with a modest amount of north-south drift. On a voyage like this, the gap between the rhumb line and the Great Circle is real but not enormous. The Great Circle track is shorter, but by a margin you could reasonably call moderate rather than dramatic, and the curve required to capture that savings is gentle. The Great Circle distance between the two ports runs a little under 3,000 nautical miles, and the straight rhumb path a naive planner might draw only stretches that figure by a relatively small percentage, which chassin albiali chassin, noticeable to a fleet operator watching fuel budgets across hundreds of crossings a year. But not the kind of gap that would strike an untrained eye as dramatic on its own. Now take a route that runs mostly east to west, at a much higher latitude, or a route between 2 points on opposite sides of a wide ocean that both happen to sit at a similar northern latitude. This is where the illusion gets dramatic. Consider a container ship traveling from a West Coast North American port to a major port in Japan. On the familiar flat rectangle, the intuitive path looks like it should run almost straight west, tracking roughly along a single band of latitude, cutting across what looks like empty, uneventful, open Pacific Ocean. That's what a straight line drawn on the map suggests. And it's exactly what most people who have never studied navigation assume a ship would do. Real ships and real aircraft flying the equivalent trans-Pacific routes do something that looks, at first glance, deeply strange. They arc northward, climbing up toward the Aleutian Islands, tracing a path that swings close to southern Alaska before curving back down toward Japan. On the flat map, this route looks like a huge, wasteful detour, bulging up into cold, stormy, remote waters far from the direct line below it. In the real curved world, it's shorter. Genuinely, measurably shorter. Because the shortest path between 2 points on a sphere at similar latitude doesn't run along that latitude. It bulges toward whichever pole is nearer, exactly the way a great circle geometrically has to. Because both ports sit at a broadly similar latitude and the crossing spans a huge stretch of longitude, the naive straight-line rum path would run almost due west for thousands of miles, while the true Great Circle arcs up toward the Aleutians, before curving back down, and on routes shaped like this, references on Great Circle sailing describe rum paths running meaningfully longer than the true shortest distance, in some cases by a margin easily measured in the hundreds of nautical miles once the full curve is accounted for. That gap alone, on a single crossing, can represent a full extra day or more of steaming time. For a large, moderately paced commercial vessel, which is precisely why no professional voyage planner would ever seriously propose sailing the straight line in the first place. If you've ever glanced at the little route map displayed on the seatback screen of a trans-Pacific flight and wondered why the plane's path curves way up near Alaska instead of cutting straight across the ocean the way it does on every map you grew up with, you were looking at exactly this phenomenon. Airlines fly Great Circle routes, or close approximations of them, because fuel is enormously expensive and shaving even a few hundred miles off a 14-hour flight adds up to real money and real emissions saved. Aviation regulators impose their own version of the search and rescue distance limit discussed earlier for ships too, a framework called Extended Range Twin Engine Operations, which governs exactly how far a twin-engine passenger jet is permitted to fly from the nearest suitable diversion airport at any point along its route. And that regulatory boundary, not just the pure geometry of the Great Circle, can nudge a transoceanic flight path slightly off the theoretically ideal curve to keep an emergency landing option within reach the entire way. Ships operate on the same underlying geometry, for the same underlying reason, even though the tools, timelines, and complications involved in ocean shipping are quite different from aviation, which we'll get into. The core fact doesn't change, depending on whether the vehicle floats or flies. On a sphere, the shortest path between two similarly widely separated points curves toward the pole, and on a flat Mercator map, that shortest path is drawn as a curve, while the longer path is the one drawn straight. This same confusion plays out constantly in miniature. Whenever someone glances at a flight tracking app and watches a plane's path curve unexpectedly toward the pole, instead of running in the straight line their mental map expects, online discussion forums and social media are full of travelers puzzled, sometimes genuinely alarmed, by watching a flight from a city like Los Angeles or New York to somewhere in Asia sweep dramatically north toward Alaska or the Arctic on the little in-flight map, convinced something has gone wrong, or that the airline is taking some strange, inefficient detour. Pilots and aviation enthusiasts explain the same geometry over and over in reply, that the curve isn't a detour at all, it's the shortest available path, and the straight line the confused traveler was picturing only looks shorter because it was drawn on a flat rectangle built 4.5 centuries ago to keep compass bearings honest, not to keep distances honest. It's, in a small and recurring way, the exact same postcard, the exact same fracture, playing out one nervous passenger and one seatback screen at a time, all across the world, every single day. Largely unnoticed as the broader cartographic story, it actually is. There's another chapter in this story that rarely makes it into the size distortion retellings, and it comes from the golden age of sail. In the middle of the 1800s, when speed across entire oceans became a matter of enormous commercial stakes, competitive pride, and sometimes life or death for a ship's crew. Fast-sailing ships called clippers, built to carry valuable, time-sensitive cargo such as tea from China or wool and grain from Australia back to European markets, made extensive use of a specific kind of Great Circle logic, even before anyone aboard would necessarily have used that exact term for it. Sailing ship captains of that era discovered, largely through hard experience rather than formal calculation, that the fastest way to cross the vast southern ocean between Europe, Australia, and back again meant abandoning the more northerly, seemingly gentler latitude and pushing their ships deep into the high southern latitudes, into bands of nearly constant, powerful westerly winds that sailors nicknamed the Roaring Forties, and further south still, the even fiercer Furious Fifties, named for the latitude bands where they blew most consistently. Riding those winds let a clipper ship complete a passage in a fraction of the time a more cautious, lower latitude route would have taken, and the entire loop connecting Europe, the Cape of Good Hope, Australia, Cape Horn, at the tip of South America, and back to Europe became known, quite literally, as the Clipper Route, or sometimes the Great Circle Route, in recognition of just how closely it tracked the shortest theoretical path available at those latitudes, bent further still by the ship's need to chase the wind rather than fight it. The cost of pushing that far south was real, and sometimes fatal. The Southern Ocean at those latitudes is famous for enormous waves, with nothing to block them as they build up an unbroken run around the entire planet, for sudden violent storms, and, closer to Cape Horn and the edges of Antarctic waters, for icebergs, calved from Antarctic ice shelves, drifting into shipping lanes with far less warning infrastructure than the North Atlantic would eventually receive after the Titanic disaster. Ships and crews were lost taking that route, and captains constantly weighed, voyage by voyage, exactly how far south, how close to the ice, they were willing to push their vessel and their crew in exchange for the speed those latitudes offered. That same trade-off is still being made today, in a much more instrumented and regulated form, in modern ocean racing. Solo, round-the-world sailing races such as the Vendée Globe, which sends competitors alone and non-stop around the planet, largely following the old Clipper route logic through the Southern Ocean, now operate under a strict, officially defined Antarctic exclusion zone, a boundary drawn specifically to keep racing yachts from pushing so far south, chasing the shortest great circle distance and the strongest following winds, that they would encounter ice and become impossible to rescue in some of the most remote, least monitored waters on the planet. Race organizers adjust the exact boundary of that exclusion zone from edition to edition based on current satellite ice tracking data, which means, in effect, that the ideal, fastest theoretical great circle path for the race is deliberately overridden every single year by an evolving real-time map of where ice actually is, not where old assumptions say it should be. Competitors and their shore-based routing teams run sophisticated weather routing software throughout the race, continuously recalculating the fastest available track against real-time weather and sea state forecasts, in a highly visible, closely followed, modern echo of exactly the same negotiation between pure geometry and real-world danger that Ice Age North Atlantic shipping lanes and 19th century clipper captains were conducting by instinct and hard experience alone. Sit with the strangeness of that for a second, because it's the exact estrangement this whole story has been building toward. The map you've trusted your whole life to represent what the world looks like doesn't just distort size. It inverts your intuition about distance and directness. The obviously direct route, the ruler straight line your eye is drawn to, is frequently the long way around. The route that looks like a wasteful, meandering detour is frequently the shortest path available. Your eyes and your training, staring at that familiar rectangle, are working against you. Part of why this illusion works so effectively on us in the first place has less to do with cartography and more to do with how human spatial reasoning actually developed. We evolved navigating small, local, essentially flat-feeling patches of the Earth's surface, forests, plains, coastlines, within sight of each other, where the shortest path between 2 points genuinely was, for all practical purposes, a straight line, because the curvature of the Earth is far too gentle to matter over walking distances. That deeply ingrained intuition, straight equals shortest, worked perfectly well for the entire span of human history, before long-distance sea voyages became routine, and it still works perfectly well for nearly everything in ordinary daily life: walking across a room, driving across a town. It simply stops being true the moment the distance involved becomes large enough for the Earth's actual curvature to matter, and nothing in our evolved sense of space warns us when we've crossed that threshold. A map builds a picture, and a very old, very reliable piece of built-in human intuition fills in the rest with an assumption that, for most of your life, has probably never once been wrong, right up until an ocean crossing quietly breaks it. It's worth pausing to ask why this happens, geometrically, because understanding the mechanism removes any sense that this is some sort of cartographic conspiracy or sleight of hand. It's just what flattening a sphere does. Imagine stretching a rubber ball flat onto a table without tearing it. You can't do it without distorting something, either the angles or the areas or the distances or some blend of all three. Every flat map of a round planet has to sacrifice something. This isn't an opinion. It's a mathematical certainty proven more than 2 centuries ago, and now called, after the mathematician who formalized it, Gauss's Theorema Egregium, his remarkable theorem. A sphere's surface has intrinsic curvature that a flat plane simply doesn't have, and no amount of clever projection can make a flat map behave in every respect, exactly like the surface of a globe. Mercator chose to preserve angles perfectly and let distance and area pay the price. Other map makers, as we'll get to later, have made very different trades. There's a simpler, more physical way to feel this same limitation, one you can actually try. Peel an orange in one continuous piece, if you can manage it, then try to press that curved peel completely flat against a table without tearing or stretching it anywhere. It won't lie flat. It cracks, splits, and buckles at the edges no matter how carefully you press, because a curved surface simply doesn't contain enough flat area to cover the same footprint once you force it into 2 dimensions. Cartographers solve the equivalent problem mathematically instead of physically, deciding in advance exactly where to let the stretching happen and what shape they're willing to sacrifice to make the rest of the surface behave. But the underlying constraint is the same one sitting in your hands over a kitchen counter. An orange peel and the surface of the Earth obey exactly the same unforgiving geometry. Given that geometric reality, here's a useful way to picture what a great circle route actually looks like without the distortion. Take a globe, an actual 3-dimensional globe, not a flat map. Stretch a piece of string taut between 2 ports on its surface. That string, pulled tight, naturally lies along the shortest path, the Great Circle. Now trace that string's path back onto a flat Mercator map, point by point. What you get is a curve, usually bowing toward whichever pole is closer to the midpoint of the journey. The rhumb line, by contrast, is the path you get by holding a single unchanging compass bearing the entire way, which on the globe traces a lazy, gradually spiraling path, technically a loxodromic curve, that would, if you never stopped, wind all the way around the globe in a widening or narrowing spiral toward one of the poles, without ever actually reaching it. Sail a rhumb line to its logical extreme and you get an infinite spiral. Sail a great circle to its logical extreme and you've simply gone the shortest possible way there is. It is a genuinely strange shape to picture once you try. Hold a globe in your hands and imagine a ship setting off from the equator on a bearing angled slightly northeast, never once adjusting its compass heading, sailing on that same unwavering bearing forever. It wouldn't sail in a straight line, and it wouldn't sail in a simple circle either. It would trace a widening, tightening spiral, a great swirling thread winding around and around the globe, crossing every line of longitude exactly once each time around, drawing closer and closer to the North Pole with every loop, forever approaching it, in principle, without ever technically arriving. A genuinely elegant, genuinely strange curve hiding inside the humble, everyday act of simply holding a compass bearing steady. None of this requires exotic mathematics to actually calculate, even if it looks intimidating from the outside. Navigators and, today, the software running inside every electronic chart system determine great circle distance and initial heading using a small set of well-established spherical trigonometry formulas, most commonly a version known as the Haversine formula, which takes the latitude and longitude of 2 points and returns the shortest possible distance between them across a sphere's curved surface, along with the true compass bearing needed to start the journey, a bearing that, crucially, keeps changing as the vessel moves along the curve. What took Menelaus of Alexandria and later Islamic astronomers genuine intellectual effort to work out from first principles now runs as a single line of code, executed instantly, thousands of times a day, on ships that likely have no idea they're relying on mathematics that old every time they calculate a route. Now, an honest question worth asking directly: if the Great Circle is shorter, why did anyone ever bother with rhumb lines at all? And why does this distinction still matter today rather than being a solved problem from the age of sail? The answer is that, historically, actually navigating a curving Great Circle route was much, much harder than navigating a straight rhumb line. And for a very long time, harder meant impractical, or even dangerous. Sailing a Great Circle requires the ship's heading to change continuously throughout the voyage. Not once, not at a couple of clearly marked waypoints, but constantly, moment by moment, as the vessel's position moves along the curve. Before satellite positioning, before computers, before even reliable methods of determining longitude at sea, continuously recalculating and adjusting a ship's heading across a multi-week ocean crossing was, for most practical purposes, not something an ordinary vessel and crew could pull off with any confidence. You needed constant, accurate position fixes to know how far along the curve you were, and for most of the age of sail, getting an accurate position fix, especially your longitude, was one of the hardest problems in all of applied science. A single degree of longitude error near the equator translates to roughly 60 nautical miles of real-world position error, and while that margin shrinks somewhat at higher latitudes, a navigator relying purely on dead reckoning, estimating position from speed, heading, and elapsed time without any external fix, could easily accumulate several degrees of uncertainty across a multi-week Atlantic or Pacific crossing, an error large enough to miss an entire island chain, or to believe a ship was safely far from a coastline. It was in fact quietly closing on in the dark. That problem, incidentally, is its own extraordinary story. Latitude was solvable early. Sailors could measure the angle of the sun or a known star above the horizon and work out how far north or south they were with tools like the astrolabe and later the sextant. Longitude, how far east or west you had traveled, required knowing the precise time difference between your current position and a fixed reference point, which meant carrying an accurate clock across an ocean in the age of pendulum clocks that could lose enormous amounts of time in humid, rolling, temperature-swinging conditions at sea. This is the problem that a British clockmaker named John Harrison spent decades of his life solving in the 1700s, building a series of marine chronometers culminating in a compact, robust timepiece, precise enough to keep reliable time across months at sea, finally letting navigators calculate longitude with real confidence. The British government took the problem seriously enough to pass the Longitude Act in 1714, establishing a board of longitude and offering a prize, up to £20,000, an enormous sum at the time, to anyone who could produce a practical method accurate enough to determine a ship's longitude within a specified margin of error after a long ocean voyage. Harrison spent the better part of his life fighting skeptical officials who favored astronomical methods over his mechanical one, before finally receiving recognition for a solution that worked. until problems like that were solved. Precisely tracking a continuously curving great circle route was, for a working merchant ship, simply not realistic. A single unchanging compass bearing you could trust and hold was worth far more than a theoretically shorter path you couldn't reliably follow. So sailors made a very sensible compromise, one that in a modified form actually survives on the bridge of modern ships to this day. Rather than sail the true Great Circle, which demands continuous heading changes, or the pure rum line, which is easy to sail but geometrically longer, navigators developed a technique often called composite sailing, or great circle sailing broken into segments. The idea is straightforward once you see it. Calculate the ideal great circle route on paper or on a specialized chart. Then chop that smooth curve into a handful of straight segments, connected at waypoints. Sail each segment as its own separate rum line, holding one constant compass bearing until you reach the next waypoint, then adjust your heading and hold the next bearing, and so on. The more waypoints you use, the more closely the jagged, segmented path hugs the true smooth curve of the Great Circle, and the closer you get to the real shortest distance, while still only ever needing to sail simple, holdable, constant bearing legs. As a practical rule of thumb still taught in navigation courses, a great circle track is often broken into waypoints spaced roughly every few degrees of longitude, close enough together that each individual straight segment barely diverges from the true curve, while still keeping the total number of course changes a watch officer needs to manage across an entire ocean, crossing perfectly manageable. This single compromise, splitting a curve into straight, compass-holdable pieces, did more to quietly shape the mathematics of global trade than almost any other idea from the age of sail. It let merchant fleets capture most of the distance savings of the true shortest path while working within the real limitations of compass and clock. And to plot those segments accurately, navigators needed a second kind of map entirely, one built for an entirely different purpose than Mercator's chart. That second projection is called the gnomonic projection, and it has a property that is, in a sense, the mirror opposite of Mercator's. On a gnomonic projection, every great circle on the globe, without exception, is drawn as a perfectly straight line. Where Mercator sacrificed distance and area to make compass bearings straight, gnomonic sacrifices almost everything else. Shapes distort savagely away from the map's center point, and you can never show more than roughly half the globe on a single gnomonic map to make the single shortest path between any 2 points appear as an honest straight line. Navigators would use a gnomonic chart specifically to plot the ideal great circle route for a voyage, mark out a series of waypoints along that straight line, then transfer the latitude and longitude coordinates of those waypoints back onto the trusty, familiar Mercator chart, where the actual day-to-day steering and plotting would happen, one straight rum line segment at a time, waypoint to waypoint. 2 different maps doing 2 different jobs, used together, each honest about the thing it was built to be honest about, and both, quietly, essential to getting a ship across an ocean by anything close to the shortest available path. That's worth remembering because it undercuts a tempting but lazy conclusion. The idea that Mercator's map is simply wrong and some other projection is simply right. It's not that simple, and treating it that simply would trade one kind of confusion for another. The mathematics underlying all of this, the formal proof that a great circle represents the shortest path between 2 points on a sphere, and the trigonometric tools needed to actually calculate one, didn't originate with Mercator or with European navigators at all. It reaches back to the astronomers of the ancient world. A Greek mathematician named Menelaus of Alexandria, working around the year 100, wrote extensively on spherical geometry, laying foundational groundwork for understanding triangles drawn on the curved surface of a sphere rather than a flat plane, work originally motivated by the very practical problem for its time of astronomy, tracking the positions of stars and planets across the dome of the visible sky. itself modeled as a great sphere surrounding the Earth. That spherical trigonometry was substantially advanced centuries later by astronomers and mathematicians across the Islamic world during a period roughly spanning the 9th through the 13th centuries. Driven in significant part by an entirely different practical need, determining the Qibla, the precise direction toward Mecca that Muslims around the world needed to know accurately in order to perform daily prayers correctly, regardless of how far away or in what direction their city happened to sit. Solving that problem rigorously, for cities scattered across a huge and expanding region, required exactly the same underlying spherical geometry that would later let European navigators calculate a great circle route between two ports separated by an entire ocean. Scholars such as al-Battani and later al-Biruni made substantial contributions to spherical trigonometry in this period, refining tools that would eventually flow through translation and centuries of transmission into the European mathematical tradition that Mercator and later navigators calculating composite great circle routes by hand ultimately relied on. The rhumb line versus great circle distinction sitting at the center of this entire story, in other words, rests on mathematics originally developed to solve problems about prayer direction and star charts, long before anyone applied it to a compass bearing across the Atlantic. There's one more layer of real-world complication worth being honest about, because it affects how precisely any of this rhumb line versus great circle theory translates into an actual heading a ship's crew can act on. A magnetic compass doesn't point at true geographic north, the fixed point around which the Earth's lines of longitude converge. It points toward magnetic north, the wandering location where the Earth's magnetic field lines converge, which sits a meaningful distance from true north and which drifts gradually but measurably over years and decades due to the slow churn of molten material inside the Earth's outer core. The angular difference between true north and magnetic north at any given location is called magnetic declination, or magnetic variation, and it's different at every point on the globe, sometimes trivially small, sometimes particularly at high latitudes near the magnetic pole itself, large enough to throw a course dramatically off if a navigator forgot to correct for it. Every rhumb line and every great circle waypoint bearing calculated from true geographic coordinates has to be corrected for local magnetic variation before a helmsman, steering by a magnetic compass, can actually use it. An extra translation step layered on top of everything already discussed. The invention of the gyro compass in the early 1900s, a spinning device that seeks true geographic north directly rather than magnetic north, eventually gave navigators a way to sidestep this correction entirely for their primary heading reference. One more quiet technological upgrade alongside satellite positioning and electronic charting that made the theoretically ideal route calculated on paper progressively easier to actually sail with precision in the real world. Ships were never the only ones who needed this exact mathematics either. When engineers set out to lay the first successful permanent transatlantic telegraph cable, completed in 1866 after an earlier attempt in 1858 failed within weeks of going into service, choosing the shortest practical undersea path between Ireland and Newfoundland was governed by precisely the same great circle geometry that governed ship routing, with the added complication of needing to account for undersea terrain, since a cable laid along the shortest surface distance is worthless if it has to be dragged across an impassable underwater mountain range or dropped into a trench far deeper than available cable and equipment could handle. The same fundamental question, what is the true shortest path across a curved ocean, quietly underwrote the birth of instantaneous global communication just as thoroughly as it underwrote the shipping routes carrying physical cargo across the same water. Let's talk about what this actually costs or saves in the real world, because the abstract geometry only matters if it touches something people actually pay for. A large modern container ship burns an extraordinary amount of fuel Depending on size, speed, and engine type, a big container ship can burn somewhere in the range of 150 to 250 tons of heavy fuel oil per day at typical cruising speed, sometimes more on the largest vessels running at higher speeds. Fuel of that kind, even before accounting for periods of price volatility, routinely costs several $100s a ton. Multiply that out, and you get a daily fuel bill that can run into the tens of thousands of dollars for a single ship on a single voyage. Now consider that a large shipping line doesn't operate one ship. It operates dozens, sometimes hundreds, running continuously across every ocean on Earth, every day of the year. Against numbers like that, the difference between a rum line and a great circle on a long, high-latitude crossing isn't academic. On some Trans-Pacific and North Atlantic routes, following an efficient great circle or composite great circle track instead of a naive straight rum line can save meaningful percentages of total distance sailed, which translates directly into meaningful percentages of fuel burned, meaningful reductions in the greenhouse gas emissions the voyage produces, and meaningful savings in the raw number of days a ship, its crew, and its cargo spend at sea instead of earning revenue at the next port. Time isn't a soft cost in shipping. A ship sitting in transit is a ship not loading, not unloading, not generating the next contract's worth of freight income. Shaving even half a day off a long crossing, multiplied across an entire global fleet and an entire year of voyages, is a genuinely large number in fuel, in emissions, and in dollars. It is worth appreciating just how much weight rides on these seemingly small percentage differences in distance, because the scale of global ocean shipping today would have been unimaginable to Mercator or to any 19th century clipper captain. The entire economics of long-distance ocean freight were transformed in 1956 when an American trucking entrepreneur named Malcolm McLean loaded a converted tanker ship called the Ideal X with 58 standardized metal shipping containers and sailed it from Newark to Houston, proving that cargo packed into uniform, stackable steel boxes could be moved between truck, rail, and ship with a fraction of the labor, time, and cost that loading and unloading loose cargo by hand had always required. Containerization, as this innovation came to be known, is arguably the single most consequential logistics revolution of the 20th century. And it's the reason a huge share of the manufactured goods, electronics, clothing, and consumer products in an ordinary household today crossed an ocean at some point, packed anonymously among thousands of identical boxes stacked on a single enormous vessel. Modern container ships built in the decades since McLean's experiment can carry the equivalent of over 20,000 standard shipping containers on a single voyage, vessels so large that their scale barely registers on an ordinary printed map, dwarfing anything Mercator could have pictured when he was solving problems for wooden sailing ships a fraction of that size. Against that kind of scale, a single percentage point of extra distance sailed, multiplied across an entire global fleet, moving the majority of the world's physical trade, stops being a rounding error and becomes one of the genuinely significant levers shipping companies, fuel suppliers, and increasingly climate regulators are all watching closely, which is exactly why the distinction between a rum line and a great circle, seemingly a piece of 16th century mathematics, remains an actively managed, commercially serious question on every one of those voyages today. That commercial pressure has only intensified in recent years, layered now with genuine regulatory weight rather than pure cost accounting alone. Following the sharp spike in oil prices around 2008, much of the container shipping industry adopted a practice called slow steaming, deliberately reducing cruising speed well below a vessel's maximum capability. Because fuel consumption rises disproportionately fast at higher speeds, meaning a modest reduction in speed can produce an outsized reduction in fuel burned per voyage. Slow steaming made the exact distance sailed matter even more than before, since a ship already spending more days at sea per voyage has even less room to absorb unnecessary extra miles without stretching delivery schedules further. More recently, the International Maritime Organization has introduced binding regulatory measures directly targeting fuel efficiency and emissions, including a global cap on sulfur content in marine fuel that took effect in 2020, and newer measures known as the Energy Efficiency Existing Ship Index and the Carbon Intensity Indicator, which require ship operators to measure, report, and progressively improve the carbon efficiency of their vessels or face operational restrictions. Under this kind of regulatory pressure, shaving unnecessary distance off a long ocean crossing is no longer just a matter of discretionary cost savings for a shipping line's finance department. It has become a measurable, reportable, regulated performance metric, which means the 16th century mathematics distinguishing a rum line from a great circle now sits quietly inside modern climate policy compliance calculations as well. It's worth making the underlying decision logic explicit, because that's precisely the kind of judgment call a modern ship's officer, or the routing software working alongside them, has to make on every long voyage, and it follows a fairly consistent branching pattern regardless of ocean or era. If the calculated Great Circle route stays within latitudes considered safe for the season, meaning clear of charted ice limits and away from any active storm system in the forecast window, the officer will typically approve a route hugging that Great Circle as closely as practical, capturing the maximum available distance and fuel savings. If the Great Circle's most poleward point, the single highest latitude point on the curve, known to navigators as the vertex, would push the ship into a zone flagged for seasonal ice risk, the plan shifts to a capped composite route instead, one that follows the Great Circle logic everywhere except near the vertex, where it's deliberately flattened southward, sacrificing some distance savings in direct exchange for staying clear of the hazard. If weather routing data shows a significant storm system or dangerously high sea state sitting directly across the ideal track, the route bends again, this time to avoid time loss slowing down in heavy seas, or worse, damage to cargo and vessel, even if that means sailing a longer path than either the pure Rum Line or the pure Great Circle would suggest. And if a choke point essential to the shortest available track, a canal, a strait, a narrow passage between islands, is closed, restricted, or judged too dangerous because of conflict or piracy, the entire calculation restarts from a different starting assumption entirely, sometimes adding thousands of miles that no amount of clever routing around weather or ice could ever claw back. None of these decisions overturn the underlying geometry. The Great Circle is still, mathematically, the shortest path available in principle, every single time. What changes, voyage by voyage, season by season, is how much of that theoretical saving a responsible ship's master is actually willing and able to bank, given everything else layered on top of the raw distance calculation. That's exactly why, for well over a century now, and especially since the introduction of digital and satellite tools, professional maritime navigation has never simply relied on a straight line drawn across a flat Mercator wall map. Ships' officers train specifically in Great Circle sailing and composite sailing as part of standard Maritime Academy curricula, learning the spherical trigonometry required to calculate Great Circle distances and waypoints by hand, long before they ever touch an electronic system that does the calculation for them automatically. The reasoning has never changed since Mercator's own era. Only the tools used to act on it have. Which brings us to a genuinely important nuance, one that keeps this story from collapsing into a simple, old bad map, new good map narrative. Because that narrative, while satisfying, wouldn't be true, and truth matters more here than tidiness. Mercator's map isn't obsolete. It is not even close to obsolete. Walk onto the bridge of almost any ocean-going vessel today and you'll find that a huge proportion of the chart's actually in daily use, including the official, legally mandated electronic navigational charts required under international maritime law. For coastal waters, harbor approaches, and countless regional passages still use conformal projections directly descended from Mercator's original insight. The reason is the same reason it always was. Near a coastline, threading between charted hazards, buoys, shoals, and other vessels, what a navigator needs more than anything is the ability to read an accurate compass bearing directly off the chart and trust it completely. Angular accuracy, the very property Mercator built his whole system around, is exactly what you want when you're picking your way through a crowded harbor approach or a narrow strait, where the difference between a safe passage and a grounding can be a matter of a few degrees of heading. Over those short distances, the size and shape distortion that plagues Mercator at a global scale barely registers, because distortion scales with your distance from the equator far more than with how many miles you're covering locally. It is really only over the very long haul, big ocean crossing scale, where the compounding curvature of the Earth makes the rum line meaningfully longer than the Great Circle, that the distinction becomes commercially and logistically significant. So modern navigation doesn't throw Mercator away and replace it with something else. It uses different tools, built on different mathematical trade-offs for different jobs, exactly the way the old paper-based composite sailing method did generations before satellites existed, just executed now with vastly more precision and vastly less manual labor. That precision arrived in stages, and it's worth understanding how, because it changes what navigating by the shortest path actually looks like today compared to a century ago. The single biggest transformation came from satellite positioning. What we now casually call GPS, formerly the Global Positioning System, reached a fully operational constellation of satellites by the mid-1990s, and for its first several years, civilian access to the system was deliberately degraded by the operator, the United States military, through a feature called selective availability, which intentionally introduced positioning error for non-military users. In the year 2000, selective availability was switched off, and civilian GPS accuracy improved dramatically overnight, suddenly putting position fixes accurate to a matter of meters into the hands of ordinary commercial vessels for the first time in the history of seafaring. The radio-based positioning systems that preceded GPS at sea, such as LORAN, short for long-range navigation, which had been in use since the 1940s, typically offered accuracy measured in the hundreds of meters at best, and required receivers to be within range of specific shore-based transmitter stations, a meaningful limitation in the middle of an ocean far from any coastline. GPS eliminated both problems at once, working anywhere on the planet's surface with no dependence on shore infrastructure at all. Before this, even skilled navigators using celestial fixes, radio beacons, and dead reckoning were working with position estimates that could be off by miles, sometimes many miles, especially after a long stretch of poor weather or overcast skies preventing celestial observation. After GPS became freely accurate, a ship could know at any moment exactly where it sat on the Earth's surface, to a precision earlier generations of sailors couldn't have imagined. That precision unlocked something that would have seemed like science fiction to Gerardus Mercator or to the composite sailing navigators who followed him. Modern ships, especially large commercial vessels required to comply with international maritime safety regulations, now typically navigate using a system called ECDIS, an electronic chart display and information system, which has been progressively mandated under the Safety of Life at Sea Convention, the primary international treaty governing maritime safety, with the requirement phased in by ship type and size across a schedule running roughly from 2012 through 2018, starting with new passenger ships and large tankers, and gradually extending to the broader global cargo fleet. An ECDIS system can calculate a genuine Great Circle route or a carefully optimized composite route, automatically, continuously updating the vessel's recommended heading as it progresses along the curve, informed in real time by GPS position data. In principle, this removes the historical need to manually chop a great circle into straight rumline segments, purely because continuous heading adjustment was too difficult to manage by hand. The computer can, if the operators choose, adjust course far more frequently and far more precisely than any human helmsman managing raw compass and clock ever could. And yet, tellingly, the underlying logic of composite sailing, breaking a curve into a series of manageable straight legs, hasn't actually disappeared, even with all this computing power available. Autopilot systems on ships still typically steer toward a specific heading over a given interval, rather than continuously recalculating a perfectly smooth curve moment by moment, partly because constant micro-adjustments waste fuel and stress the steering gear, and partly because human oversight of a voyage plan benefits enormously from clear, distinct waypoints a watch officer can monitor and verify, rather than an unbroken, ever-shifting curve that's much harder for a human being to sanity check by eye. So today's route plans typically still look like Mercator-era composite sailing tracks, a great circle calculated by computer instead of by hand and mnemonic chart, then broken into a practical series of rhumb-line legs between waypoints, sailed and monitored much the way sailors did it 200 years ago, just with the tedious trigonometry handled instantly, and the position fixes accurate to a few meters instead of a few miles. The tool changed enormously. The underlying compromise, curve for accuracy, straight segments for practicality, has proven remarkably durable, because it was never really a limitation of old technology in the first place. It reflects something deeper about how ships are actually steered, and how humans actually plan and verify complex routes, that computing power alone doesn't simply erase. There's a second, less famous kind of map illusion worth understanding here, because unlike the rhumb line and Great Circle distinction, this one has caused real, documented groundings in relatively recent maritime history, and it shows that projections aren't the only way a chart can quietly mislead a navigator. Every nautical chart is built on top of something called a geodetic datum, a mathematical model describing the precise shape of the Earth and a reference framework for assigning latitude and longitude coordinates to it. For most of the 20th century, different regions and different national hydrographic offices built their charts on different local datums, each one a slightly different best-fit approximation of the Earth's true shape for that particular region, optimized for local accuracy rather than global consistency. That regional patchwork worked reasonably well as long as ships were navigating primarily by comparing visible landmarks, radar returns, and dead reckoning against a chart built on the same local datum used to survey that chart in the first place. It became a genuine hazard once satellite positioning arrived. GPS reports coordinates using a single global reference system called WGS-84, and a position fix from a GPS receiver plotted directly onto an older paper chart built on a different, older local datum, can be offset from the chart's own coordinate grid by a meaningful distance, in some documented cases, by several hundred meters. Several hundred meters sounds small on an open ocean crossing, and it usually is, but it becomes extremely dangerous near a coastline, a reef, or a narrow channel entrance, exactly the places where the smallest positioning error carries the largest consequence. Maritime safety authorities have documented real groundings and near misses traced directly back to this kind of datum mismatch, crews trusting a GPS-derived position plotted onto a chart that was never built to align with it. A sobering reminder that the honesty of a map isn't only about which projection was chosen, but about whether the coordinate framework underneath it actually matches the tool being used to read it. Modern electronic charts are built directly on the WGS-84 datum specifically to eliminate this exact category of error. One more quiet but consequential upgrade sitting alongside satellite positioning and computerized route planning in the long list of things that had to be fixed before the theoretically shortest path calculated on paper could be trusted, without reservation, on the water. It helps to picture what all of this actually looks like on the bridge of a real ship, rather than only as lines on a chart. A second officer beginning a voyage plan for a long ocean crossing doesn't simply draw a line between departure and arrival on the electronic chart display and call it done. The planning process typically starts with the system generating a proposed Great Circle track automatically, calculated instantly from the entered departure and arrival coordinates using exactly the spherical trigonometry inherited from centuries of accumulated navigational mathematics. The officer then checks that proposed track against a series of overlays, the latest ice charts if the season and latitude warrant it, current weather routing recommendations from the company's contracted routing service, known areas of piracy risk or geopolitical restriction, traffic separation schemes near any coastlines the route passes close to, and the vessel's own performance characteristics, since a smaller or more weather-sensitive ship might need a more conservative track than a large, stable one. Where those overlays conflict with the pure Great Circle, the officer adjusts the track by inserting or moving waypoints, effectively hand-tuning the same kind of composite sailing compromise that navigators have been making for centuries, just now visualized instantly, rather than plotted by hand with parallel rulers and dividers on a paper mnemonic chart. Once approved, typically by the ship's master, the finalized route becomes a sequence of waypoints the autopilot will steer between, each leg its own short rum line, the whole sequence together approximating as closely as safety and practicality allow, the true shortest curve available between two ports that might be separated by an entire ocean. The elegant mathematics and the messy real-world compromises aren't, in other words, two separate stories. On a real bridge, they're the same conversation, had fresh voyage after voyage, every single day, on every ocean on Earth. If any of this sounds too abstract to trust without seeing it, it's worth knowing that you don't actually have to take it on faith. Nearly every large commercial vessel on Earth broadcasts a continuous stream of position data through a system called the Automatic Identification System, originally required for collision avoidance, and a number of publicly accessible websites and apps aggregate that data into live, freely viewable global shipping maps. Pull one up and trace an actual vessel's track across the North Pacific or the North Atlantic over a period of days. And the curve we've been describing stops being a diagram and becomes something you're watching happen in close to real time. An actual ship, actually bending its course northward exactly the way the geometry says it should, thousands of miles from where a straight line on a classroom map would have told you to look. The logical endpoint of this whole progression, from hand-plotted rum lines to computer-generated Great Circle tracks, is already being tested on actual water. The Yara Birkeland, a fully electric container ship built in Norway and put into limited operation in the early 2020s, was designed to run without a crew at all for at least part of its short coastal route, navigating and avoiding traffic using onboard sensors and the same underlying route optimization logic already laid out here. Monitored remotely from shore, rather than steered by officers physically standing on a bridge. It operates on a short domestic route rather than a transoceanic one, and autonomous ocean crossing shipping remains for now experimental rather than routine, but it represents the furthest current point along a line that runs directly back through ECDIS, through the gyro compass, through Edward Wright's tables, all the way to a sailor on a wooden ship trying to hold a single compass, bearing steady across open water for the first time. Now, here's where the story gets genuinely more interesting than pure geometry, because in the real world, no ship ever sails the mathematically ideal shortest path either. And understanding why takes us into weather, ice, politics, and a surprisingly recent history of disaster and disruption. Start with weather and ocean currents, because these introduce a further wrinkle on top of the rum line versus Great Circle question, one that shows the shortest distance isn't even always the goal. The true objective for a commercial voyage is rarely shortest distance, in a pure geometric sense. It's closer to least time, least fuel, and least risk. And those aren't always the same thing as the shortest possible track through open water. A Great Circle route across the North Atlantic might be geometrically shortest, but if it drives a ship straight into the teeth of a strong headwind, or fights against the powerful eastward-flowing current of the Gulf Stream when traveling westbound, the vessel may burn more fuel and take more time following that shortest path than it would following a slightly longer route that rides favorable currents and avoids the worst weather systems. That's exactly the job of weather routing services, a specialized industry that emerged over the past several decades and now relies heavily on satellite meteorology and sophisticated computer modeling. Companies in this field continuously ingest weather forecasts, sea state data, and ocean current models, then calculate what is often called the least time track for a given voyage, a route that may weave meaningfully off the pure Great Circle line specifically to catch a favorable current, avoid a developing storm system, or dodge dangerously high waves that would force the ship to slow down for safety anyway. The tools behind this kind of routing have grown considerably more sophisticated in recent years. Modern weather routing providers ingest data from weather satellites, ocean buoys, and numerical forecast models running on supercomputers, and increasingly apply machine learning techniques trained on huge historical archives of past voyages, fuel consumption logs, and weather outcomes, refining their recommended tracks continuously as a voyage actually unfolds, rather than simply issuing a single fixed plan at departure. Shipping companies that have adopted this kind of dynamic, continuously updated routing report meaningful fuel savings compared with static, pre-planned routes, with industry sources describing improvements that, depending on the route, the ship, and the season, commonly fall somewhere in the rough range of a few percent up to somewhere near 10% of total voyage fuel consumption, savings that compound significantly across a large fleet running thousands of voyages a year. A ship's master, working with this routing guidance, is constantly balancing the elegant, idealized geometry of the Great Circle against the messy, ever-changing reality of the actual ocean surface it has to cross. The Gulf Stream alone can add or subtract a knot or two of effective speed, depending on whether a ship rides with it or fights against it. And over a multi-day crossing, that difference compounds into real hours saved or lost. The Pacific has its own equivalent in the Kuroshio Current, a powerful warm water flow running north past Japan that plays a similar role in trans-Pacific voyage planning. One more reason the routes ships actually sail along. That Aleutian bulging Great Circle rarely trace the mathematically perfect curve exactly, bending slightly one way or another to catch or avoid these enormous, mostly invisible rivers, moving within the ocean itself. Neither current is an isolated phenomenon. Both form part of much larger, basin-spanning circulation patterns called ocean gyres, enormous, slow-rotating loops of current driven by wind patterns, and the Earth's own rotation, one filling most of the North Atlantic, another filling most of the North Pacific, quietly shaping water temperature, marine ecosystems, and shipping economics across an entire ocean basin at once. A reminder that the water a ship crosses is never actually still. Never a blank blue background the way it appears on a printed map, but a moving, structured system. A good routing plan has to read almost the way a pilot reads the sky. The very language used to describe sea conditions in these routing decisions has its own navigational history worth a brief mention. The standardized scale still used today to describe wind strength at sea, running from flat calm at the low end to full hurricane force at the top, was developed in the early 1800s by a Royal Navy officer named Francis Beaufort, and adopted as an official standard by the British Admiralty in the 1830s specifically so that ship captains across an entire navy could report and compare sea conditions using a shared, consistent vocabulary rather than each relying on a personal, subjective sense of what counted as a strong wind. That same Admiralty, over the following century, became one of the primary institutions producing the standardized nautical charts, built on Mercator's conformal foundation, that eventually spread across the world's merchant fleets alongside British maritime trade itself. Then there's ice. And here the story connects to one of the most famous maritime disasters in history, in a way that's genuinely instructive rather than just dramatic. In April of 1912, the RMS Titanic, operated by the White Star Line, struck an iceberg in the North Atlantic and sank, killing more than 1,500 people. The disaster is often remembered, somewhat unfairly, purely as a story about a supposedly unsinkable ship and a fatal collision. It's also, less famously, a story about shipping routes and the tension between speed and safety on the North Atlantic crossing. In the years before the disaster, competing shipping lines had been engaged in an informal race to offer the fastest possible Atlantic crossings. And one contributing factor in the Titanic disaster was the ship's continued high speed through a region where ice warnings had already been received, on a track that, while common for the season, sat close enough to the seasonal ice limit to prove fatal. The response to the disaster changed North Atlantic navigation in a way directly relevant to everything we've been discussing. In 1914, the International Ice Patrol was established, originally under the United States Revenue Cutter Service, and today operated by the United States Coast Guard, with the specific mission of monitoring iceberg locations in North Atlantic shipping lanes and issuing warnings about the seasonal limits of ice danger. Shipping companies, working through international agreements on recommended tracks, adjusted the standard North Atlantic shipping lanes to shift further south during the iceberg season, deliberately choosing routes that were, in pure geometric terms, longer than the theoretical Great Circle or even the practical composite Great Circle track, specifically to keep ships well clear of the higher latitude waters, where icebergs calving off Greenland's glaciers tend to drift into the shipping lanes each spring. The North Atlantic track system born out of this response is redrawn twice a year even now, shifted between a more northerly summer configuration and a more conservative, ice-avoiding winter and spring configuration, with the exact coordinates published through official notices to mariners so that every vessel crossing that ocean is working from the same current, seasonally adjusted map, rather than a single fixed line drawn once and never revisited. That's a vivid, human example of a broader and very important truth. The shortest path calculated purely from spherical geometry isn't automatically the path a responsible ship actually sails. Think of it as a starting point, a baseline, the real route, then gets adjusted against, sometimes only slightly, sometimes dramatically, to account for danger, weather, politics, and economics that no map, however accurately projected, can encode by itself. The Great Circle tells you the shortest possible distance available in principle. It never tells you the wisest distance to actually sail, and conflating those two ideas has, historically, had fatal consequences. Ice isn't the only hard limit that reshapes theoretical routes into real ones. Consider choke points, the narrow passages through which an enormous share of global maritime trade is funneled by simple geography, regardless of what any projection or Great Circle calculation might otherwise suggest. The Suez Canal, connecting the Mediterranean Sea to the Red Sea through Egypt, is perhaps the most consequential of these. Without it, a ship traveling from Europe to Asia would have to sail all the way around the southern tip of Africa, past the Cape of Good Hope, adding many thousands of miles and roughly 1 to 2 additional weeks to the voyage, depending on the specific ports involved. The canal itself opened in 1869, a massive engineering undertaking led by French diplomat and developer Ferdinand de Lesseps, and its completion instantly rewrote the practical shipping map of the entire world, collapsing a route that had defined European trade with Asia for the preceding 3 centuries, down to a fraction of its former length overnight. The canal exists precisely because pure Great Circle geometry, which knows nothing about continents blocking the way, is useless without a functioning understanding of actual land masses. And because the economic value of cutting a multi-week detour down to a matter of hours Transiting a canal is almost impossible to overstate. More than 1/10 of all global seaborne trade, by some widely cited estimates, transits the Suez Canal in an ordinary year, making it one of the single most consequential choke points on Earth, in a very literal, physical sense. The fragility of that arrangement was demonstrated dramatically in March of 2021, when the container ship Ever Given, a vessel roughly the length of 4 football fields laid end to end, ran aground diagonally across the canal, blocking it entirely for 6 days. The backup of waiting vessels stretched for miles in both directions, delayed an estimated $10 billion or more of global trade for every day the canal remained blocked, and forced shipping analysts, many of them for the first time in their careers, to publicly reckon with just how much of the modern global economy depends on a single, roughly 200-meter-wide channel of water functioning correctly. A second, more recent and ongoing example makes the same point from a different angle. Beginning in late 2023 and continuing into the following years, attacks by Houthi forces in Yemen on commercial vessels transiting the Red Sea and the narrow Bab el-Mandeb Strait leading toward the Suez Canal led many of the world's largest shipping lines to make a striking decision. Rather than risk their vessels and crews in that corridor, they chose to reroute a substantial share of Europe to Asia traffic entirely around the Cape of Good Hope, deliberately choosing the far longer 19th century route over the shorter, canal-based 20th century one, adding roughly 10 to 14 additional days and thousands of extra nautical miles to affected voyages. This wasn't a navigational error or an oversight. It was a conscious trade, accepting substantially higher distance, time, and fuel cost in exchange for substantially lower risk. The same fundamental calculation the North Atlantic ice lane shift represented a century earlier, just driven by a different kind of danger. That rerouting carried real consequences on the other end too, for a country whose economy leans heavily on canal traffic. Suez Canal transit fees are a significant source of foreign currency revenue for Egypt, and the sustained drop in traffic during the Red Sea disruption translated into a documented substantial decline in the Canal Authority's reported annual revenue compared with prior years. A reminder that a shipping route is never just an abstract line on a chart. It is also, at either end, a real flow of money that real governments, ports, and workers depend on. And a decision made for safety thousands of miles away in the Bab el-Mandeb Strait shows up weeks later in a national budget. Notice the pattern running through the Titanic-era ice lanes, the Suez choke point, and the Red Sea rerouting. In every one of these cases, the actual real-world route a ship sails is the product of layering several very different kinds of information on top of the pure geometric baseline the Great Circle provides. Physical obstacles like continents and canals, seasonal hazards like ice, and human threats like piracy or conflict. The map showing you the shortest theoretical path is only ever the opening bid in a much longer negotiation between geometry and reality. Every additional layer, weather, ice, war, canal capacity, chips away at or reroutes that idealized line, sometimes by a little, sometimes, as with Cape of Good Hope rerouting, by a genuinely enormous margin. Panama offers a related but distinct case worth mentioning, because it shows that even a solved choke point isn't immune to disruption. The Panama Canal, connecting the Atlantic and Pacific without the far longer alternative route around the southern tip of South America via Cape Horn, opened in 1914 after a construction effort, led in its successful phase by United States Army engineers, that had to overcome not just the physical challenge of cutting a channel through mountainous terrain, but a public health crisis. Since an earlier French attempt at the same canal had collapsed decades before, partly due to devastating losses from yellow fever and malaria among the workforce, diseases whose mosquito-borne transmission was only properly understood and brought under control in the years immediately before the American project succeeded. It depends on a system of locks fed by fresh water from Gotten Lake. In 2023 and into 2024, a severe regional drought reduced the lake's water levels so significantly that canal authorities were forced to impose draft restrictions, limiting how deep, and therefore how heavily loaded, transiting ships could be, and reducing the total number of daily transits allowed. Shipping companies had to adjust schedules, sometimes lightening cargo loads or choosing alternate routes entirely, because a choke point everyone had treated as a fixed, dependable feature of the map turned out to be dependent on rainfall patterns increasingly affected by a changing climate. The lesson generalizes. The shortest path a map or a satellite navigation system calculates is only ever as reliable as the assumptions baked into it, and those assumptions, canal capacity, ice extent, political stability in a given strait, can and do shift. Suez, Panama, and the Red Sea are far from the only places on Earth where geography simply overrules whatever a great circle calculation might otherwise prefer, and it's worth naming a few more, because together they show just how much of the world's shipping map is really a network of narrow, negotiated bottlenecks, rather than the open, freely curving ocean a satellite photo might suggest. The Strait of Hormuz, a narrow channel separating the Persian Gulf from the Gulf of Oman and the wider Indian Ocean, sits at the exit point for a very large share of the world's seaborne oil exports, commonly estimated at somewhere around 1/5 of global oil consumption passing through it in an ordinary year, making it a choke point watched more closely and threatened more often than almost any other stretch of water on the planet, where geopolitical tension involving the nations bordering it can send ripples through global energy prices within hours. The Strait of Malacca, running between the Malaysian peninsula and the Indonesian island of Sumatra, connects the Indian Ocean to the Pacific and carries an enormous share of trade flowing between Europe, the Middle East, and East Asia, particularly energy shipments bound for China, Japan, and South Korea, and has historically been a significant zone of concern for piracy, given how narrow and heavily trafficked it is at its tightest point. And the Bosphorus, the strait running directly through the city of Istanbul and dividing Europe from Asia, is so narrow in places that large vessels transiting it pass remarkably close to shoreline buildings, and its use is governed by a nearly century-old international agreement called the Montreux Convention, signed in 1936, which still regulates which naval vessels from which nations may transit it and under what conditions. A striking example of how a physical choke point's rules can remain governed by mid-20th century diplomacy, even as the ships passing through it and the cargo they carry have utterly transformed. Every one of these narrow passages exists on the map as a fixed point. No great circle calculation can route around. A place where the elegant curve of spherical geometry simply has to yield to the shape of the actual continents in the way, and where a huge share of global trade funnels through gaps that, in some cases, are only a few kilometers wide, carrying a volume of goods that would be almost impossible to imagine if you'd never traced the actual shipping lanes rather than just the coastlines on a map. There's one more quiet layer shaping real-world routes that rarely makes it into popular explanations of great circle sailing, and it has less to do with geometry than with risk management. Marine insurers and classification societies, organizations such as Lloyd's Register, which has been inspecting and certifying the seaworthiness of ships since the 1700s, along with modern search and rescue coordination requirements under international maritime law, all factor into how far from established shipping lanes and rescue infrastructure a vessel's owners and insurers are willing to let it stray. Even when a pure great circle calculation might suggest cutting through a more remote stretch of open ocean, a route that ventures too far from established search and rescue coverage or too far outside the areas where a nearby vessel could reasonably be diverted to assist in an emergency can affect a ship's insurance terms, its compliance with the Global Maritime Distress and Safety System framework that coordinates rescue communications worldwide, And in some cases, it's legal permission to carry certain cargo at all. That's one more reason the tidiest, shortest theoretical Great Circle is treated, across the entire industry, as a starting hypothesis rather than a final answer, a baseline that gets weighed against ice, weather, choke points, piracy, and now quietly but persistently, the practical question of how far help would actually have to travel if something went wrong. Let's widen the lens for a moment, because the Rum Line and Great Circle story, as central as it is to the title's promise, is really just the most consequential example of a much larger truth about maps in general, and understanding that larger truth is what lets you see every map you encounter for the rest of your life a little more clearly. Every flat map of the Earth is a compromise, and every compromise is, in a real sense, a decision about what to lie about. This sounds harsh, but it's simply mathematically unavoidable, a direct consequence of that theorema egregium mentioned earlier. You can't flatten a curved surface without distorting something, so every cartographer, going all the way back past Mercator to the ancient Greek geographers who first grappled seriously with representing a spherical Earth on a flat surface, has had to choose which properties to preserve and which to sacrifice. Mercator chose angles, at the cost of area and distance, particularly toward the poles, because he was solving a navigation problem. Other map makers, working on entirely different problems, have made very different choices, and looking at a few of them side by side is genuinely useful because it dissolves the misleading idea that somewhere out there exists a single, correct flat map of the world. If only cartographers were smarter or more honest. There is no such map. There can't be. There are only maps, each honest about a particular thing, and dishonest, in a technical but real sense, about everything else. Take the projection known as Gall-Peters, first proposed in a form by a Scottish clergyman named James Gall in the mid-1800s, then independently reintroduced and popularized in the 1970s by a German historian named Arno Peters, who marketed it heavily as a corrective to what he characterized as the political and even implicitly colonial bias baked into the Mercator worldview, given how dramatically that projection inflates wealthy, high-latitude nations in Europe and North America while shrinking equatorial nations, many of them in Africa, South America, and South Asia, that were historically colonized by exactly those inflated northern powers. Gall-Peters preserves area accurately. Every country's shape on the map genuinely occupies a footprint proportional to its real size on Earth. The cost of that honesty about area is honesty about shape. Continents on a Gall-Peters map look stretched and distorted, tall and narrow in ways that look unfamiliar, and to many eyes trained on Mercator's proportions, simply wrong, even though, in terms of relative area, it's Mercator, not Gall-Peters, doing the actual misleading. This projection gained real-world attention in 2017 when Boston Public Schools announced it would begin using Gall-Peters-style maps in some of its classrooms, specifically to give students a more accurate sense of relative country sizes, a decision that generated a notable amount of public discussion about just how much an ordinary wall map quietly shapes a person's sense of which parts of the world matter more. Or take the Robinson projection, created by an American geographer named Arthur H. Robinson in 1963, which doesn't try to perfectly preserve any single property, not angles, not area, not distance, but instead aims for a reasonable, visually pleasing compromise across all of them, simultaneously minimizing the worst distortions of each, rather than eliminating any one entirely. The National Geographic Society adopted the Robinson projection as its standard reference world map from 1988 until 1998. A decade in which millions of students and readers absorbed a subtly different sense of the world's proportions than either the Mercator or Gall-Peters crowd would have gotten. In 1998, National Geographic switched again, this time to the Winkel triple projection, originally developed by a German cartographer named Oswald Winkel back in 1921, which similarly aims to average and minimize several kinds of distortion at once, rather than perfectly preserving any single one, and which remains to this day the reference projection more atlases and classrooms default to than any other. And for something that pushes the whole concept further still, consider the orthograph projection, developed by a Japanese architect named Hajime Narukawa and awarded Japan's prestigious Good Design Grand Award in 2016. Rather than projecting the globe directly onto a flat rectangle, the way Mercator and most traditional projections do, orthograph divides the sphere's surface into a large number of small triangular faces, projects those faces onto the surface of a tetrahedron, and then unfolds that tetrahedron flat, an approach that manages to keep every landmass and every ocean much closer to its true relative area and true relative shape than almost any traditional rectangular projection, at the cost of an unfamiliar, somewhat puzzle piece looking overall outline that takes a moment to mentally adjust to. Precisely because it refuses to force the round Earth into the tidy rectangle we've all been culturally trained to expect a world map to look like. Some cartographers even leaned directly into the peeling problem rather than fighting it. The Good Homolocene projection, developed by an American geographer named J. Paul Good in the 1920s and used for decades in a widely distributed school atlas bearing his name, Deus Melibis Manenis Barinismi, deliberately slices the map apart along several ocean boundaries, presenting the world's landmasses as a set of separate petal-shaped lobes with gaps torn open across the blue of the ocean between them. Essentially an unpeeled orange rendered honestly as an unpeeled orange, rather than forced into a single, unbroken rectangle. It preserves area quite accurately and avoids much of the shape distortion cylindrical projections, like Mercator suffer near the poles, at the obvious cost of a map that looks fractured and incomplete at first glance, oceans interrupted mid-span by the sheer edges of the projection. It's a strange trade to make for most everyday purposes, and yet, for a story specifically about how a map can quietly hide the true shape of an ocean crossing, there's something fitting about a projection that simply admits, visibly, on the page, exactly where the flattening had to tear. One more projection deserves real attention here, less for its mathematics than for what its creator was explicitly trying to make people feel, which lines up almost perfectly with what this whole story has been building toward. In 1943, the American inventor and architect Buckminster Fuller published what he called the Dymaxion map, unfolding the surface of the globe onto the flat faces of an icosahedron, a shape with 20 triangular sides, in a way that keeps the relative size and shape of every landmass remarkably close to accurate, with none of the polar inflation that plagues Mercator. Fuller's deeper goal, though, wasn't simply mathematical accuracy for its own sake. He wanted to break the deeply ingrained, almost invisible cultural habit of looking at world maps with a particular hemisphere centered and a particular orientation assumed as natural, north conveniently on top, continents treated as the meaningful shapes and oceans as the featureless blue gaps between them. The Dymaxion map can be unfolded and rearranged in several different valid configurations, and one especially striking version presents nearly all of the Earth's major land masses clustered together as something close to a single connected island group, surrounded by one continuous, unbroken world ocean, rather than the familiar picture of separate oceans, an Atlantic here, a Pacific there, each cordoned off politely between continents. That reorientation isn't just a novelty, it's in a real sense, a more honest picture of the actual medium ships move through. Water covers roughly 70% of the planet's surface, and beneath the labels we assign to different named oceans, it's genuinely one continuous, interconnected body, joined at every coastline, every strait, every choke point already discussed. A container ship leaving Rotterdam bound for Singapore doesn't experience a hard border, where the Atlantic supposedly ends and the Indian Ocean supposedly begins. It experiences one long, continuous stretch of water, curving with the planet the entire way. And Fuller's odd, unfamiliar triangle-paneled map, precisely because it refuses to hand you the tidy, compartmentalized ocean labels your school atlas trained you to expect, comes closer to representing that lived, physical reality than almost any conventional world map ever has. There's a useful, almost playful tool cartographers use to visualize exactly how any given projection distorts things at any given point on the map, called Tissot's indicatrix, named after the 19th century French mathematician Nicolas Auguste Tissot, who developed it. The idea is simple. Imagine placing a small, perfectly identical circle at regular intervals all over the surface of a real globe. Then run those identical circles through whatever projection you're examining and see what shape and size they come out as on the flat map. On a genuinely conformal projection like Mercator, every one of those circles stays a perfect circle, no matter where you place it. But the circles grow dramatically larger the further from the equator you go, visually confirming the area distortion in the clearest possible way. On an equal area projection like Gall-Peters, every circle stays exactly the same size no matter where you place it, but the circles near the poles get squashed and stretched into flattened ellipses, visually confirming the shape distortion instead. Look at a set of Tissot indicatrices laid over any world map, and you can read, at a glance, exactly what that particular projection is being honest about, and exactly what it's quietly choosing to distort in exchange. A few other specialized projections round out the picture, and each one exists because somebody somewhere needed a map honest about a particular property that neither Mercator, nor Gall-Peters, nor Robinson happens to preserve. The azimuthal equidistant projection, centered on a single chosen point, keeps both true compass direction and true distance accurate from that one central point to absolutely anywhere else on the map, at the cost of increasingly severe distortion the further you move away from the center. It's the projection centered on the North Pole, chosen for the blue and white emblem on the flag of the United Nations, a deliberate symbolic choice suggesting a view of the world with every nation equally, radially accessible from a shared center point. Amateur radio operators use the same kind of projection, centered on their own home station, for a very practical reason. It lets them read off, at a glance, the true compass bearing and true distance to any other station on Earth they might be trying to reach by bouncing a signal off the atmosphere. The stereographic projection, another conformal option alongside Mercator, preserves angles and local shapes with similar honesty, but handles the poles far more gracefully, making it a common choice for polar exploration charts and for maps focused on the Arctic and Antarctic regions specifically, exactly the high-latitude territory where standard Mercator becomes practically useless. And then there is the projection responsible for the map living inside almost every smartphone on Earth right now, quietly reshaping the mental image of the planet for a generation that may never have unrolled a paper wall map in a classroom at all. Web Mercator, the specific variant used by Google Maps, Apple Maps, and the vast majority of other digital mapping platforms, is a close mathematical cousin of Mercator's original 1569 projection, chosen for reasons that have nothing to do with 16th century sailors and everything to do with computer engineering. A conformal cylindrical projection divides the world into square tiles that can be endlessly subdivided and reassembled with simple, fast mathematics as a user zooms in or scrolls around, which made it, decades ago, by far the most computationally convenient choice for the earliest web mapping engineers building systems that needed to render smoothly on limited processing power and slow internet connections. That engineering convenience, not any navigational virtue, is why thumb-swiped digital maps today distort the relative size of countries in almost exactly the same way Mercator's original chart did In some respects, even slightly more severely, because Web Mercator uses a simplified spherical formula rather than Mercator's more precise ellipsoidal calculation. Every viral social media post marveling at how small Alaska, Greenland, or Scandinavia actually are compared to how they appear on a phone screen is, whether the person posting it realizes it or not, rediscovering the exact same 1569 trade-off just delivered through a touch screen instead of a canvas sail chart 450 years later, for a population overwhelmingly unaware that their phone map was never trying to be honest about size in the first place. Interestingly, the platforms most responsible for spreading that illusion have already quietly begun correcting for it at one specific zoom level. In 2018, Google Maps updated its web mapping product so that when a user zooms all the way out to view the entire planet at once, the display switches away from flat Web Mercator and renders an actual three-dimensional rotatable globe, instead showing every landmass at its true relative size and shape, before switching back to the familiar flat, tiled Mercator projection the moment a user zooms into street level for actual turn-by-turn navigation. That single design decision, largely unnoticed by most users who encountered it, is a small-scale, everyday echo of exactly the same dual system already described here for ocean navigation. One honest projection for the big picture, an entirely different honest projection for practical, close-range use, switched between seamlessly depending on the actual task at hand. This cultural dominance didn't happen purely by engineering accident either. Long before smartphones, Mercator's rectangular, north-up orientation had already become the default visual shorthand for the world across television news broadcasts, military briefing rooms, and printed atlases throughout the 20th century, largely because a simple rectangle divides and tiles cleanly for layout designers, fits neatly onto a television screen or a page, and matches the north-up orientation most audiences already expect without needing any explanation. Once a particular shape of the world becomes the unquestioned visual default across enough newspapers, enough classroom walls, and enough televised weather reports, it stops being experienced as one projection among several reasonable choices and starts being experienced simply as what the world looks like. Exactly the quiet, cumulative process that let a 16th century sailor's tool become nearly everyone's mental image of the planet, navigational purpose and all its distortions included, largely unexamined. None of this means every projection is equally good for every purpose, and it would be a mistake to slide from every map distorts something into a lazy, shrugging relativism where no map's choices matter. They matter enormously, and matching the right projection to the right job is precisely the skill at the center of this entire story. You wouldn't want a ship's navigator plotting a coastal approach on a Gall-Peters chart, where angles are subtly wrong everywhere, any more than you'd want a middle school geography class building its entire mental model of relative national size and importance from a Mercator wall map, where some nations are inflated many times over relative to others, purely because of where they happen to sit on the globe. The point isn't that all maps are equally true or equally false. The point is that every map is true about something specific and silent, sometimes misleadingly silent, about everything else. And the only real defense against being quietly misled by a map is knowing which specific thing that particular map was actually built to be honest about, which loops us back, deliberately, to the ocean and to ships. Because there's one more genuinely significant, still unfolding chapter in this story, one that didn't exist in Mercator's era, or even in Titanic's era, and has only become a live, real-world navigational question within the last couple of decades. For most of recorded history, the Arctic Ocean has been functionally closed to ordinary commercial shipping for most of the year, locked under thick, permanent sea ice that made anything beyond specialized, icebreaker-escorted expeditions impossible or absurdly impractical. This mattered enormously for our Great Circle story because two of the most tantalizing theoretical shortcuts on the entire planet, the Northern Sea route running along Russia's Arctic coastline and the Northwest Passage threading through the Canadian Arctic archipelago, sit directly along some of the shortest possible Great Circle paths between major ports in Europe, North America, and East Asia. A Great Circle route between, say, a Northern European port and a major East Asian port often wants to bulge dramatically northward, exactly the same geometric bulging we saw in the Trans-Pacific example earlier. And in the most extreme cases, that bulge wants to cut directly through Arctic waters rather than around them. The Northwest Passage in particular carries a weight of history that makes its slow, partial reopening genuinely striking rather than merely a footnote in shipping logistics. For centuries, European explorers searched for a navigable route through the Canadian Arctic connecting the Atlantic to the Pacific, a shortcut that, if it existed and were usable, would have offered exactly the kind of dramatic Great Circle shortcut already at the center of this story, and the search cost a great many lives along the way. The most famous of these attempts, the 1845 expedition led by British Royal Navy officer Sir John Franklin, departed with 2 well-equipped ships and more than 120 crew members, and simply vanished. Search expeditions over the following decades gradually established that the ships had become trapped in ice, and that the entire crew, including Franklin himself, ultimately perished, in what became one of the most haunting mysteries in the history of polar exploration. The wrecks of Franklin's 2 ships weren't located and confirmed until 2014 and 2016, respectively, nearly a century and a half after the expedition disappeared, found through a combination of Inuit oral history, painstaking archival research, and modern sonar survey technology. For most of the age of steam and diesel shipping, this theoretical shortcut simply didn't matter, because the ice made it impossible in practice regardless of what the geometry suggested. Over the past several decades, however, satellite observation has documented a substantial, measurable decline in Arctic summer sea ice extent, driven by a warming climate, and that decline has begun opening genuine, if still limited and highly seasonal, windows during which specially ice-classed commercial vessels, sometimes still requiring icebreaker escort, can transit routes like the Northern Sea route during the summer months in a way that would have been essentially unthinkable a few generations earlier. This is not, it is important to be honest, some kind of imminent replacement for the Suez or Panama canals, or for the Great Circle and Rumb Line calculations governing the vast majority of ordinary global shipping. Arctic transits remain a small fraction of total global maritime trade, constrained by a short, seasonal window, expensive ice-class vessel requirements, limited search and rescue infrastructure in the region, and substantial uncertainty about long-term ice conditions from year to year. But the trend is real, it's measured, and it has triggered serious, sustained geopolitical interest, particularly from Russia, which controls much of the coastline along the Northern Sea route and has invested heavily in Arctic infrastructure and its own icebreaker fleet, and from other nations, including growing interest from China, weighing the strategic and commercial value of new shipping corridors that, if they continue opening further, would represent the most significant new addition to the map of practical global sea lanes in generations, a route straight through the exact high-latitude region that Mercator's own map distorts most dramatically, and that his conformal projection was originally built to help sailors navigate around, not through. That same passage that swallowed Franklin's expedition without a trace saw a genuinely historic first in September of 2013, when the bulk carrier Nordic Orion became the first large commercial cargo vessel to transit the Northwest Passage fully loaded, carrying coal from Vancouver to Finland, a route that saved the ship a significant number of sailing days compared with the traditional path through the Panama Canal, precisely because it captured a large share of the Great Circle-style shortcut the passage had always represented in theory, and had never, in practice, been safely usable for. That single voyage doesn't mean the passage is now routine, ordinary commercial traffic. Ice conditions remain unpredictable year to year. Insurance and ice-class vessel requirements remain demanding, and most shipping companies still treat it as a marginal, closely watched option rather than a dependable standard route. But it stands as a real documented marker of exactly how much the map of what is navigationally possible has already begun to shift, in a region where, for centuries, the map's promise of a shortcut only ever delivered mystery and loss. There's something almost poetic in that, if you sit with it. The part of the map most stretched and most exaggerated by Mercator's 500-year-old mathematical trade-off, the high Arctic, ballooned on paper into an impression of a vast, ice-locked, essentially unusable expanse, is the same part of the actual physical Earth now becoming slowly and unevenly a genuinely relevant piece of the shortest path puzzle for the first time in human history. The map's oldest illusion and the ocean's newest reality are converging on the exact same patch of the globe. Let's step back and take stock of what we've actually built up here, because it's worth assembling the pieces into one coherent picture before we close. You started this story with an image you've carried since childhood, a rectangular world map, familiar continents in familiar proportions, a straight line drawn confidently between two ports as the obvious, direct, sensible route across an ocean. That image wasn't malicious, and it wasn't stupid to hold. It was built by a 16th century cartographer solving an extraordinarily real, extraordinarily dangerous problem, letting sailors hold a single compass bearing across open ocean and trust it, at a time when trusting the wrong bearing could mean starving to death, lost hundreds of miles from anywhere. But that same map, precisely because it makes constant compass bearings look straight, quietly makes something else look straight that has no business being straight: the impression of the shortest path. The straight line on your childhood wall map is a rhumb line, a path of constant direction, not a geodesic, not the true shortest track a ship or a plane would actually want to fly or sail across a genuinely long ocean crossing. The real shortest path, the Great Circle, usually looks like a curve on that same map, often an unintuitive, poleward bulging curve that looks, to untrained eyes, like a mistake or a wasteful detour. It is neither. It is simply what the shortest distance between 2 points on a round planet looks like once you flatten that planet using a tool built to keep compass bearings honest rather than to keep distances honest. From there, we followed the consequences outward, the way they actually ripple through the real world. Composite sailing, breaking that ideal curve into practical, holdable straight segments, born out of necessity in the age of sail, and, strikingly, still the basic shape of how modern computer-guided ships plan their routes today, even with satellite precision available. The staggering fuel and time costs riding on these small differences in distance, multiplied across a global shipping fleet that never stops moving. The layers of real-world complication, weather, ocean currents, ice limits shaped by the memory of the Titanic, canal choke points vulnerable to a single grounded ship or a multi-year drought, security threats capable of rerouting entire trade lanes around an entire continent that stand between the clean geometry of a great circle and the actual track a responsible ship's master chooses to sail. And finally, the wider recognition that Mercator's trade-off was never uniquely wrong or uniquely deceptive. It was one specific, historically brilliant choice among many possible choices, sitting alongside Gall Peters, Robinson, Winkle Treaple, Autograph, and others, each honest about something different, each silent, in its own particular way, about something else. Here's the recognition this whole journey has been building toward: the one meant to genuinely change how you see a map from now on. A map isn't a photograph of the Earth. It never was. And mathematically, it never could be. A map is an argument, a specific, deliberate claim about which properties of the real, round, three-dimensional world matter enough to preserve, and which properties the map maker has decided you can afford to have distorted in exchange. Mercator's argument was that sailors needed honest angles more than they needed honest sizes, and for the specific, brutal life-or-death problem he was solving, he was completely right. The mistake was never Mercator's. The mistake, one that persisted quietly for centuries and still shapes how billions of people picture their own planet, was letting a map built to answer one very specific navigational question quietly become the default, unquestioned answer to every question, including questions about relative national size and questions about which route across an ocean is actually the shortest one. Next time you see a straight line drawn across a map, whether it's a shipping company's promotional route graphic, a kid's atlas, or the mental image you carry around in your own head of how the world is shaped, ask yourself a simple, useful question. Straight according to what? Straight as a compass bearing? Honest about direction, but often dishonest about distance? Or straight as a great circle? Honest about distance, but only appearing straight on a completely different kind of map built for that specific honesty? The line itself can't tell you which kind of truth it's offering. Only knowing which map you're looking at and why that map was built the way it was can tell you that. Picture, for a moment, what an honest satellite view from directly above the North Pole would actually show you, looking straight down at the planet the way no flat rectangle ever quite manages to. From that vantage point, the real tracks of ships crossing the North Atlantic or crossing the North Pacific between North America and Asia wouldn't look like straight lines cutting across a flat sheet of graph paper at all. They would look like gentle arcs bowing toward the pole beneath your feet, each one tracing, as honestly as three-dimensional geometry allows, the genuinely shortest path available between two ports thousands of miles apart. That image, the true shape of a ship's shortest crossing, is the one you now carry that most people never will, and it was hiding inside the most familiar map in the world the entire time, waiting for someone to ask the straight line what it was actually made of. There's a broader habit of mind worth carrying away from this too, one that extends well past maps. Almost every simplified model humans build to navigate a complicated reality, a map, a schedule, a set of rules of thumb, a spreadsheet formula, is built to be honest about one specific thing, for one specific purpose, at the cost of quietly distorting everything else. That's not a flaw to be embarrassed about or eliminated. It's the only way simplification ever works at all. The danger was never in Mercator building a tool that traded distance for angle. The danger only ever appears at the moment a specialized tool, built to answer one question honestly, gets treated as the final, complete answer to every question, long after everyone has forgotten which specific question it was actually built to answer in the first place. Experienced navigators tend to describe this entire body of knowledge less as a set of rules memorized once and applied mechanically, and more as a kind of layered instinct built up over years. The Great Circle as a starting sketch, the weather and the ice charts, and the insurance limits and the political map of which straits are safe this month, as a series of corrections laid over that sketch, until what remains is a route nobody could have drawn purely from geometry alone, and nobody would trust purely from instinct alone either. It's that combination, cold mathematics and hard-earned judgment, working together rather than in competition, that actually gets a ship, and everything stacked in its containers, from one side of an ocean to the other. Picture the bridge of a ship somewhere in the middle of an ocean crossing right now, at whatever hour it happens to be, on the other side of the world. Somewhere out there, a watch officer is glancing between a radar display, a weather overlay, and a chart showing a route that, if you traced it on the flat rectangle you grew up with, would look like a lazy, unnecessary curve, bending north for reasons the map itself never explains. It is not lazy, and it is not unnecessary. It is centuries of solved problems, hard lessons, and quiet mathematics, folded into a single line on a screen, doing exactly what it was built to do. If this changed how you look at the next map you scroll past, or the next flight tracker showing a plane curving strangely up toward the pole, instead of running straight across an ocean the way you expected, that's genuinely the point of tracing the whole thing out. If a straight line has been quietly lying to you your entire life without your noticing, tapping that like button is a fair trade for finally catching it in the act. If you want more of this kind of unraveling, the sort of thing that takes something you've looked at 1,000 times without really seeing and turns it inside out, subscribing is the simplest way to make sure the next one finds you. And if you've got a favorite example of a map lying to you in some other way entirely, a projection, a border dispute, a distance that never quite matched what you found once you actually crossed it, drop it in the comments, because some of the best follow-up stories this channel has ever told started exactly that way, with someone pointing out a distortion nobody else had thought to mention yet. The ocean hasn't changed. The ships haven't changed. Not fundamentally, not in the geometry that governs how far apart two ports actually are. What's changed is the picture in your head of the line connecting them, and that's a small shift to carry around, but it's also, in its own quiet way, exactly the kind of thing that makes the rest of the map, every map, a little more legible from here on out.